Thanks so much for joining this lunchtime talk. We have Josh Skinner here from Omni Clean Air, and we also have Emily Liu on the line, who is an engineer with Omni, to answer any questions in the chat. And of course, we have Robert Booth here, the co-author of ICRA 2.0, to discuss with Josh some negative air and exhaust challenges. We're going to cover 5 topics, and we're going to sprinkle in questions throughout. We're going to talk about sizing and placement of equipment at the beginning of a project, how to determine which equipment to use and how many machines you might need, HEPA filtration, how to properly choose a HEPA filter and how to verify that it's working properly, verifying that the room is holding negative, common issues that we see, why containments lose pressure, and then some troubleshooting. So with that, Bob, I'm going to let you go ahead and jump in.
Thank you, Livia. So thanks for joining us. This is a special talk. When we teach the ICRA class, one of the biggest challenges that we have and students have are how to properly decide what the negative air pressurization should be for a construction area. So if you're familiar with ICRA 2.0, we did not put a negative air requirement in that standard, which is table 5. We put in there based on the hospital's policy. So the reason we did that is we really couldn't come to any consensus. Basically looked at the literature and decided that it was best chosen from the hospital group. Now, I survey a lot of hospitals and work with a lot. I see everything from 0.01 negative pressure, that's inches of water, to 0.05. 0.03 is the Canadian standards that we reference when we talk about this in the class. 0.01 being the negative air requirements for the CDC for TB isolation rooms or special respiratory isolation. Personally, I don't think that's appropriate. However, I do see that from time to time. The literature shows that 0.03 to 0.05 is protected, but it's really up to the hospital. So negative pressurization gives us that indication at the door or the entrance to the facility that's being constructed that the space is under negative pressure. And one thing that we see as a challenge, and one thing we put in the ICRA 2.0 as well, is that the pressurization is not on a single room or anteroom, but it's on the space. So negative pressure is what we want to control. We want to make sure that nothing gets out of the space. It is hard to control sometimes, and we're going to talk about that over the next half hour, 45 minutes when we talk about different challenges. And then we also see readings drift back and forth, similar to what we see with an isolation room. It's really up to the organization. Now, I do a lot of litigation, so when I'm looking at this data, I look and see what is the practice that the facility uses to monitor and measure this. Just like we have ORs, that we have variations in temperature and humidity, we also have variations in pressurization. So with the construction area being under complete negative pressurization is what we're trying to achieve. So how are negative air contaminants removed and how does that work? Well, one thing that we specifically put into the ICRA 2.0 guideline, which was really always the requirement, is that it has to be drawn from clean to dirty, which dirty is our air inside the construction area. And it has to draw from cascading from the anteroom, if you have one, or the outside area into the construction area, and that the whole space is negatively pressurized. We don't expect a construction area to be completely clean from negative air. That's not the goal. The goal is to remove contaminants so that when you leave those spaces, you don't have tons of dust. Otherwise, we wouldn't have negative air. We just do some recirculation of air in that space, which is not appropriate. One challenge I see is that some organizations think that a air mover or a machine that's just circulating air is negative pressurization, and that is absolutely false. So one thing we want to remember is to get negative air, you have to take air out of that box or out of that space and take it to another area. ultimately, we want you to bring that outside the space, outdoors, away from any other areas, but that's not always the case. Sometimes you have to exhaust indoors. Sometimes you exhaust to another area of lower hazard than a occupied space. However, that is the challenge that we have when we're removing air from that box. So remember, to get proper negative air, it can't be just an anteroom that's under negative pressure. It has to take all that air out of the space and take it from that construction area and exhaust it outdoors. So a couple nuances to remember here. Air is drawn inward. It comes underneath the door, just like when we have our negative air rooms and our isolation rooms in the hospital, or as we do positive rooms for ORs, it blows out. So we're measuring that air that's being sucked in. If it's going to go through a HEPA filter or if it's going to be exhausted outside, one thing that we want you to remember is it has to go through a HEPA filter if it's within 25 feet of an outside air intake. The other item there that we see challenges with, and I know Josh will talk more about this and Emily will too, that when you're exhausting into another space, you have to make sure that is HEPA filtered, but you also have to verify that on a routine basis. And then some of those pressure issues can be of concern. So exhausting outside needs to be clean, whether it's within 25 feet of an outside air intake or a building entrance or another window. So part of the ICRA process is to look at where that exhausts out to, but make sure you're not affecting the building at all. So those are the main topics that we want to think about for negative pressurization and where to position. So let's talk about topic number one, and that's airflow and movement and placement and where you put these items at, these negative air machines. And as you can see in the slide here, this is a negative air device or air mover that's attached to a flex duct that goes outside. So we want to make sure that we get the appropriate air changes in that space. But we're not trying to get 100% air changes, but we're trying to get some achievable air changes in the space and get good negative pressurization. There are some engineering calculations that you can use. People smarter than me would be able to do that and say, okay, if you have a room this big and you want that negative pressure of 0.03, here's how many machines you need. However, I use a basic calculation, which we're going to go over next, about how to calculate the CFMs that you need. The position of the machine should not be right at the door, but should be in a window or an exhaust area if you're going outside at the other end of the space. Okay, and the reason that is we're trying to get all the dust in that construction area and remove it, cascade it away from entrances into occupied spaces. If we had no occupied spaces attached to a construction area, we really don't need negative air because we're not affecting those indoor areas. That's illustrated in the ICRA process under where we put that little asterisk to say if you can totally contain the space like a shell space and you're not going in those areas and it's totally contained, you don't need negative air. But if you do, we want it to cascade out. And then the route, as we mentioned earlier, should go away from building openings, HEPA filtered again if it's within 25 feet of an outside air intake. We don't want that getting back into the building and discharges to a safe area where there's no occupants or anything like that.
How about exhausting inside of the building, Bob?
Well, one thing that we addressed when we updated the ICRA process is, and it's listed in Table 5, that if you exhaust indoors, people have been doing it for years, and we know that. If you exhaust indoors, we want you to verify that it is HEPA filtered. So you see this device over here with the little flex duct on there and a HEPA filter maybe inside. We want you to verify that. And the way you verify that, we'll talk a little bit more, I think, down the road and a couple topics later. But you're going to verify that it reduces the particulate at an achievable portion that a HEPA filter would, which be 99.97% at 0.3 microns. And that basically is that we get good filtration through the device. The way you measure that is if you're going to exhaust indoors, which really we don't like to do that because there's odors and smells and chemicals and stuff like that. And I know Josh is going to talk a little bit more about HEPA filter versus some types of media that you can use. But basically, if you have to exhaust indoors, you have to verify that it is HEPA filtered. So the way you do that is with a particle meter And we put that in the standard as well, that a particle meter should be able to verify that you're getting good reduction.
If you could talk a little bit about this calculation, I think it's helpful for looking at the size of the room you have and deciding what you.
Yeah, the basic calculation that we have used for years in engineering, most facilities managers know, is the air changes per hour calculation. And so when we go into an OR or a solid utility room where we're trying to calculate the air changes per hour, we use the calculation that's on the left here, and that's the CFM that you're measuring from a supply or a return diffuser times 60 divided by the volume of that room. So CFM, that calculation you get with using a bolometer or some kind of measuring device to give you cubic feet per minute. For supply would be for positive pressure rooms. For returns or exhaust would be used to calculate your air changes for a negative air room. So in that case, we can convert that or derive the same equation from this calculation on the left to give us CFM. So basically, you got CFM is going to, or cubic feet per minute needed volume times the air changes that are desired by 60. So I put a simple calculation in here. So if you are working in a room that's 20 by 20 with a 10-foot ceiling, that would be 4,000 cubic feet. And if we had 6 air changes per hour, which would be a minimum desired air changes, and I'll tell you, a lot of times engineers or the people that are doing this work don't even think about air changes, but they should. Then you get the calculation comes out that you need 400 CFM from those machines. So what that means is when you go back to look at the machine, Olivia, that is being put in there, how many machines you need is basically the question. Josh, you might want to jump in on this. How many CFMs you get from a standard machine? So I've seen where you'll have 4 or 5 of those machines positioned blowing out a window, okay, when they could have done it with a bigger one type machine. Any comments about that?
Well, I mean, I think you hit on a few important pieces there. My biggest comment is you talked about 6 air changes per hour. I think that's one of the biggest thing that we see missed is defining what that minimum air changes is. And at least in my experience, 6 is the minimum for sure that anybody's going to want to work with. There is no standard to my knowledge. I've seen hospitals at 10 or even 12, but I would say working with at least 6 is what everyone should strive for. And then to your point, using multiple machines versus one larger machine, I think that's something where contractors struggle with. They don't either understand what airflow or what CFM a machine can do. They're also often looking at when they go get a machine that's 2000 CFM, they don't understand that that's peak and that's not standard CFM on that machine. That's not what it's actually producing. And so they'll go and they'll start a containment and realize they're not actually hitting the negative pressure that they need. And it's because they're actually underpowered on machines. So I agree with you, like less that are pumped more is better. And I always encourage give yourself some wiggle room, give yourself the ability to go up and have more CFM ability than what you think you need, because you're oftentimes building this whole calculation off of a false number. And that false number is that peak number. What a company will advertise a machine is like, great, it does this, but that's actually not what it's doing all the time. That's what it's doing at its very best. And instead understand what that machine is. Do I suggest a preference? I tend to suggest 1 or 2 larger machines versus 15 smaller machines is probably the better route to go. Not only for you're able to achieve the higher CFM, but also it's easier to monitor to make sure you're getting proper airflow on less machines and making sure that you have the filters than having to have someone go around and be responsible to check all these machines and make sure they're all working at optimal performance.
And I mean, I've seen everything, Josh, from a big fan in a window, believe it or not.
Yeah.
And it works. I mean, it actually works. So, a big gigantic fan or some kind of other air moving device But what I see is a big delay that our staff have when they go to check these things is that the contractor really didn't do the calculations on the room.
Mhm.
And then they have leaks and stuff as well. So a couple other things I
Yes.
wanted to mention is getting that negative pressurization in that room is affected by a number of things. And I just saw this at a facility a couple of weeks ago where they didn't close off the supply vents for that space. So they were getting a number of CFMs from cooling in that space that they had to overcome. So they could never really achieve negative
Yep.
air. The other is they didn't have a proper barrier, which is what we talked about in the last
Mm.
class that we talked, our last office hours is about good barrier protection. And so they're drawing from those spaces up in the ceiling, and you're basically the same thing we do with our ORs and our negative air machines, negative air rooms, that we have to have those sealed up really tight. So we want the same thing to go on.
I think this is a good flow into the next topic, which is HEPA filtration, because you talk about that ideal number that the machine hits, but that's only if the HEPA filter isn't overloaded. And I want to ask you, Josh, how do you know when your machine's starting to get overloaded? How do you know when to change the HEPA filter? And what are the challenges you see with that?
I think there's a couple things there. And, if we take it back to the start, Robert touched on it earlier. Like, one, do you have the right HEPA filter? So at least 99.97 efficiency, bare minimum. And we're seeing more and more hospitals moving up to giving themselves 99.99 as the minimum requirement. And the reason there is it gives you more coverage, cleaner air, etc. So that's piece number one. Piece number two is metal frame has got to be everybody's standard when it's anything to do with hospital and patient care. Wood frame or particle board HEPA filters are they're less stable, they're less structurally sound, and they just have more problems, and you get leakage, and then doesn't matter, not all the air is going through the HEPA, so therefore you're not hitting the efficiency you needed to. So that's piece one. How do we start off sound? Piece two is, are we overflowing the machine? So we've been on sites and seen, there's the horror stories of people that forgot to put the HEPA in the machine in the first place and then been feeding out into the hospital. That's the worst case scenario. But on the flip side of that, you have contractors trying to be too efficient. They're putting in the wrong filters or too many pre-filters before there, and they're actually clogging up airflow, all with the best intention of great. More filters means cleaner air, better efficiency, but they're actually preventing airflow and CFM in the first place. So if all of those are done right, if you're using the recommended pre-filters, you got the right HEPA in there, then how do you know? Well, what most people don't understand is from day one, the moment you turn that machine on, you're officially clogging up the airflow. Every minute that machine's on, you're pulling in particles and you're starting to clog up there and reduce efficiency. A good machine, most machines will have a little light that comes on and tells you. The problem is you're assuming that your contractors are looking for that light. We recommend a regular schedule. Just go in there, go through a regular schedule. Pre-filters changed at least as often, in most cases, weekly, depending on level class 5 or class 4 containment, and HEPA filters changed on a regular schedule. So then you're never in a place where you're worried, is this overclogged? Is this done? Yeah, the light will come on in theory, but when machines don't always get treated the greatest, they get beat up, lights get ignored. If you have your team on a regular check schedule and using a checklist, that's the best way to secure that every machine you have is never getting clogged up. And with that checklist schedule, you're doing a visual inspection. You're visually inspecting the pre-filters. Does this need to be changed? You're visually inspecting the HEPA. Is there damage to the HEPA medium? Two easy ways to say, I might have changed this HEPA a month ago, but it's been damaged. And if it's damaged, it's letting stuff through it shouldn't have let through.
Yeah, you're right. I mean, and this is a great topic, Olivia. And a lot of times when when a contractor brings in a machine, they go, "Oh, is there HEPA filters already in there?" And I go, "Okay, when's the last time you changed it?" Well, like Josh mentioned, the minute you put a HEPA filter in, it gives you some kind of static pressure decrease. So we do the same in our air handlers for our hospitals, but we want you to put in a filter and then record the pressure drop, which is usually about a half an inch. And then most manufacturers say another inch and a half, you want to change it. Because like Josh mentioned, HEPA filters get more efficient as they get loaded. We know that, but eventually they pass their life and they're not able to give you that CFM. This is one reason we don't put HEPA filters in supply diffusers, because you get a big pressure drop in CFM. So it's not efficient to do that. We do it back at the air handler where we can do it. A couple things here before we go on to the next topic. Yes, 6 to 12 is some recommendations. As Josh mentioned, there's no standards. What we did put in ICRA 2.0 in Table 6 is that you follow the hospital's policy on air changes in that space and at completion of the job. I know some big organizations have those in there. I think Nemoris and the VA have different air change requirements at the completion to remove particulate. Because what we're trying to do, that's a very effective here, is at the end of the project, you're just not going to shut the project and say, okay, let's go back to work. Let's bring everyone in. You need to bring those particulates down to an achievable level that are not going to harm anybody and the space is clean. And then, as we mentioned earlier, you have to put in your guideline of your policy what the negative air requirements are, 0.01 to 0.03, and then how to measure the HEPA filtration. I will tell you, I get a little pushback every once in a while, and some of my colleagues are like, we're never going to have HEPA filtration. That's not achievable. I disagree. It is at the beginning. And what we want you to do is look at the whole system and making sure that you get an achievable drop before you start construction. So the importance here is when you set these things up, you should measure at the intake of the device and where you're exhausting it to, and making sure that you get a good reduction.
Let's talk a bit about actually disposing of those HEPA filters when they're loaded up. Some of these projects, you may be pulling in mold, possibly. When you're pulling out a HEPA filter that's loaded with all of this debris and possibly contaminants, how do you dispose of that properly?
Well, we want to follow good industrial practices, and there's a process called the bag in and bag out that we use in a hospital for isolation risk, because we don't want our facilities management engineers and HVAC folks to get exposed to some of the contaminants that could be in a filter. Now, basically, we know that a HEPA filter will encapsulate a lot of harmful particulate, but not viruses and not bacteria all the time. So the best way is to take that to an area where there's no patients, wear some kind of respiratory protection if you think there's contaminants such as molds and other items. If you're doing asbestos, we want you to follow those guidelines, which are HEPA filtered respirator and personal protective equipment to remove those. But in the case of common construction debris, we want you to good industrial practices, and then you wrap it up and you throw it away. Is it biohazardous? No, absolutely not. It can go into the regular trash as long as there's no biohazard contaminants suspected. So, yeah, that's a great question. We want people to understand. Josh, you got any comments on that?
No, I think you hit it right. You bag and tag it. Why go through all the effort of making sure that you're preventing all the contaminants from the space to be locked down through a HEPA and then walk it out with not being locked in a bag and carried through patient areas? You're literally defeating everything you just accomplished. Put it in a bag, tag it up, get it out, get into a garbage where it's in open airflow and away from everybody safely.
Yeah, and that should really go for any pre-filters as well. So that's why we have those devices inside the construction area, and we don't have them outside the construction area, because we know we're going to have contaminants. That's a great question, but we're trying to contain that all inside. One thing that I see a lot is when they change those filters out, they say, okay, we have HEPA filters here, but the device is really dirty, and then it doesn't pass the particulate sampling because basically contaminant got all into the device, and then it's going down the ductwork, and they really can't show that the particulates are reduced. So we ask that you clean that as well.
When do you recommend particulate counts be taken on these types of ICRA projects?
Oh, you had to ask that question. So we didn't put, thank you. We did not put in the guideline. We say you develop a process for that. And I know we're going to teach a particle count class coming up in a couple of our other sessions talk about that. But basically, that's going to be up to the hospital. I recommend that at the beginning of the project, you verify it's HEPA filtered, right? And then also at a periodic time based on the hazard of that area. So if you're in an operating room, I would check the particles every day. If you're exhausting into an operating area, it might be a lower risk area, and you're comfortable that the machine is working properly, then you can do it on a weekly basis. Most people do verify that on a routine basis, anywhere from a day to 3 days to a week. So it's based on hospital policy.
That's a whole hour discussion, but I wanted
Oh
to.
my God, it's a whole. I mean, I have some thoughts on that. I mean, I'm a worrywart, so I want to make sure that we cover everything and make sure everything's in process, which is why we like these types of advice that Omni has here with monitoring pressurization on a routine basis. So I'm going to let Josh jump on this one, verifying pressure.
All right, Josh, I'll throw a question at you. So, how do you verify? What are the different methods of verification? And what is the preferred method, do you think?
I mean, I'm biased, but this is an easy one for me, Robert. The Omni IQ series is, I firmly believe, is industry leading. We built a machine that we built for the hospital team and the contractors, because what we've been seeing over the years is that the technology kind of flatlined and didn't continue to grow with the needs of the market and didn't grow to meet ICRA 2.0. At the end of the day, while I jest and I joke that, like, buy our machine, we firmly believe it's the best. You want to calibrate it, and I think that's a very operative word that is under invested on. The market is flooded with thousands and thousands of various versions of digital differential pressure monitors. But the biggest miss we see over and over again is that annual calibration. And so people are using 5-year-old machines that have not been calibrated in 5 years, and when they come in to get calibrated, they're drastically off the first time that they've ever been calibrated. So really what you're doing is you've been taking records and making assumptions off of a machine that's just false. But a digital machine, ideally, that has records to prove, outside of just once a day, someone went and looked and signed a piece of paper saying that we were in negative pressure for the 30 seconds I looked at this, but something that's pulling regular records to show and prove, and defensible records, auditable records that can say, we stayed in negative pressure while we were working in this containment at a reasonable period of time. Outside of that, I have lots of best practices, making sure there's machines near every entrance, ideally, in and out of that space, so that you're monitoring not just in one spot far, far away. Because I've been on containments where whole floor is under construction and they have one pressure monitor at one entrance, but there's 5 other entrances that people come and go through that are very far from that first entrance.
Let me chime in there.
Yeah.
No, those are. That's why I wanted you to start. Well, let me look at the other side of this. So I'm going to go back to when this was originally developed in the beginning of 1994 into 1995. And it basically just says you need to monitor negative pressure and define what that is under the original ICRA form. And we put in there that we think that you need to have some kind of device that measures the actual value of that pressure, and come up with a process on how you're going to verify that that's always continuous. So yes, these type of devices, and the way I came across to meeting Josh and Emily is that I had a client that was struggling with pressure all the time, and they couldn't record and they couldn't get alarms. And these devices are so clever these days that they do that. They alarm to you. They tell you that something's going on, and they let you know that you need to go address it. And people have been challenged with that for the last 20 years. So there's all kind of monitoring devices. So there's a manometer, which is what I was taught in graduate school to use, which is like a little liquid filled device that costs about $30, and you put it on the wall, but it's not, it's continuous, but you don't know if something goes out of range. There's the continuous monitors, as Josh mentioned, that's been around for some time, that do a very good job. And what I've seen a lot of my clients do is they'll say, give us the reading for the case of litigation might come up. But if you don't read those readings, it's just like anything else. You didn't see that there was a variation. And I've done cases where I've been in court and I've said, well, I'm looking right here and it says on this day that you missed all these readings. You didn't do anything about it. So what happened? And then there's the smoke test or the tissue check, which we don't like to use anymore. And then there's other things such as a vein anemometer or a magnehelic, or there's all kind of devices. So what we want facilities to do is pick what they think is reasonable to defend that they can document. Daily checks. I like the continuous because then I have no question about it. And if it alarms, it tells the engineer or somebody that's monitoring the PM or the project manager that there's an issue, and then there's no case about it. If I do a 1-day manometer reading or a magnehelic, then I don't know if that happened 24/7 or was just at that moment in time. And then smoke test really doesn't tell me anything. It just tells me it's negative. Tissue check doesn't tell me anything. It just tells me it's negative, and we want to know what the actual pressure was that was listed in the policy and procedure, which is required. Back to Josh's comment, yes, you should have these somewhere, not at the door particularly, but that measures the whole room. So a lot of times I'll say, just put it on the wall for the room, outside the wall somewhere. It doesn't necessarily have to be at the entrance, but people want it at the entrance because that's where they go to write the monitor down, the readings down, or go look at it and make sure it's negative. But you want to verify that the pressure is actual negative for the whole space. Problems I've seen with that, Josh, Olivia, is that they put the tube some space, it goes into the ante room only. And so you're measuring differential pressure between the outside area versus the inside and getting that pressure change in these devices, such as the Omni device and others. And basically it just says, here's where it's at. Sometimes that tube gets clogged up. Sometimes it, doesn't get put in the right position. So you want to monitor that. And back to your point, Josh, we do that in the hospitals as well. We calibrate these devices on a annual basis. And I've used that as a defense in the past, or saying, hey, well, did you do this? And why didn't you monitor this? Just like we do with the HEPA filters and the machines, you gotta maintain them and make sure they're good. So good, that's for verification.
That goes with any piece of equipment. We work in hospitals. We help develop particulate monitoring programs for hospitals, and they'll say, oh, we'll just give a particulate monitor to one of our guys. He'll go check it. This particle meter is, 10 years old. It's never been calibrated. It's not defensible. So what we've seen a lot of our hospital clients do with all of their equipment is purchase it and maintain it in-house. So you're not counting on your contractor to come in with some of this equipment. You maintain it in-house. So if you're using different contractors for different projects, they're using the correct equipment.
Well, let me say one more thing there. What we preach when we're talking about developing your ICRA or your construction policy, which is what you're supposed to do, we tell the facility of the organization, define what you want. What do you want? If you're telling your contractor you're going to do work for us, now you need to have one of these devices. Let them know that right up front. So when they're bidding the project, they know they're going to have to go out and get these things. We get a lot of people saying pushback. I didn't know I had to buy this device. I mean, they're not really that expensive and they're very useful and you can use them project to project, but basically let them know what they have to do. And so that when somebody like myself as the infection control come along and say, where's your Omni device? Where's your alarms? What are you doing? Then they have that already defined. Okay. Next topic. Why containments lose pressure. There's a couple of reasons here that we want to talk about. You want to start off, Josh?
Yeah, I mean, this list could probably be 10x longer. We've seen and heard it all. I know you physically probably caught many of them, and we get contractors that call us with mysteries of this keeps happening at this time of night, every night. We don't know why. In my experience, at least for me, the number one reason is a door gets left open for a couple reasons. Contractors are coming, going, they don't close it all the way. You use a good system like Stark, but they're not making sure they invest in an incredibly good wall system and then they don't close the door, kind of defeats the purpose. So that's piece number one. We also see that people get curious with containment sites. So 8 o'clock at night, someone's walking by and opens the door to look to see what's happening in there. And then that person from the hospital or patient or visitor leaves the door open. So number one is it's something simple like a door got left open. And so now we're not maintaining negative pressure. Number two, I agree, leaky barrier is a huge one. It's one that's underinvested, and that's the one that we tend to get the mysteries from. When you talk like the smoke test, when you talk about what's going on, your covered vents is such a story that we've taken to heart. We had contractors like, 10 o'clock every night, the alarms are going off. What's going on? Why do we keep seeing this happen? And then we're looking at the trackable report and we see it going. Well, sure enough, there's a leak in the roof containment. Usually the AC machine is shutting off or turning on at the time, and that's what's causing it. And they didn't do a great job of covering those vents. So there's a lot of them that we could go down. I could probably tell you a bunch of horror stories, and you could probably tell me a bunch of horror stories. But those are when we tell someone to go look, that's usually the first places we say go look before we go anywhere else.
Yeah, I know we hit on it earlier when I talked about one of the requirements we put in the table 5 under these types of precautions is you have to isolate supply and return. And contractors don't want to do that, especially in Florida where I live. I know you're in Seattle and it's not as hot, but you're telling me it's getting hot there today. But basically, we have contractors that use some of that cooling from the supply from the existing HVAC system.
Yeah.
And that's prohibited in the guidelines. So we basically put in there you can't use anything for recirculation in an active air handling unit. But also the reason we want you to close and the supply and return is so that you're not affecting that space with other systems that you're going to have to overcome. That's a big challenge. And I hear that every week. I hear say, well, how am I going to do that? If I cover it up, it's going to be bowing out and I can't get it isolated. I know that's a problem. You have to work that through in the pre-planning stages of the project. How are you going to isolate that HVAC system? Big projects, they're demoing a lot of that. So sometimes they can cap it off, but then that overpressurizes other areas. And that's a whole other topic altogether. But yes, that leaky barriers, anti-rooms that are left open, exhaust circulation systems that aren't effective, loaded filters, and then my favorite, which I found once, and this is one of the times in my career I just about lost it, where the contractor was shutting off the air moving machines at the end of the day. Because they said, well, we're not doing anything. Well, yes, you are, and you can't do that. And one contractor was shutting it off at lunchtime because they wanted to take, a sleep break and they didn't want all the noise. So these are things that we have to communicate with the contractor. It's simple things. It makes sense, but we need to let them know it needs to be continuous and those, so we don't want that loss of pressure. What we're trying to do here with pressurization, as we mentioned from the beginning of the presentation, is we're trying to contain that space and not affect any other areas around the other area.
And you're talking about losing pressure here, but how about like too much negative pressure and how that can impede on a project?
Yeah, I get asked that all the time. I have a picture in the slide deck that I use when I'm teaching the ICRA class about negative pressurization, too much. So I get asked all the time, how much is too much negative air? So there's no guideline, but my guideline is anything that affects other areas, and that's generally about an inch of pressure, negative air. I don't know what your thoughts are, Josh, but so in our isolation rooms and in our, the reason we put those pressurization limits in our pharmacies is because if you draw too much negative air from another space into an area, you're going to affect that space. So if we're at 0.3 negative air pressure inches of water, if you have too much negative air, maybe like a full 1 inch, you're going to really start affecting other areas. And we see that all the time where an adjacent area is now under positive pressure when it should have been negative, or it's affecting other spaces. So again, back to the guideline, anywhere between 0.08 to 1 would be one that we'd want to try to stay away from and try to keep it right in that range that we want.
Fully agree. I think if we were to use simple context, you get 0.08 to 1, you're getting the yellow, you get above 1, and you -1, you're getting in the red space. You're getting really, really dangerous for potentially affecting everywhere else around you. And the whole point of what we're trying to do is to not affect all the space around us. Between particle sampling, between maintaining, literally the whole goal is, even using a good temporary wall, is to make sure that we have an unaffected space surrounding the containment space.
Yeah, I've seen spaces at 1.5 inches, and I'm like, why are you doing this? And it's the old adage, more is better, but really it isn't.
I want to talk about the negative air is falling. You're not able to maintain it. What is our order of operations? What should we be looking at? And how do we fix it?
Well, so if you're troubleshooting and you find that you're not keeping the negative pressure that you designed, if you weren't at it in the first place, then I would recommend that you go back and do your calculation. And this is something maybe Emily could chime in on, but basically that calculation of how much CFM you actually need is not, again, always determined. So back to what we talked about earlier in the presentation, you should really plan for what that negative air system should look like, meaning what kind of negative air machines I'm going to use, how much air changes I'm going to desire, and what I'm going to have at the end of the project to make sure I can get that done. One thing that we see with delays is that the facility is ready to take down precautions, right? And they're done with the work. But the policy says you should have this many CFMs, and the contractor didn't really do that very well. Another thing that we look for when we're walking a space and negative air is not being achieved is, again, what we were talking about a minute ago, where there was gaps, holes, penetrations in the barrier. Negative air is not being achieved because you're introducing too much supply from another system, as we mentioned. There's a change in the process, happens a lot, like they added on another room to the project and they thought they were going to use the same negative air devices, or even the position is in the wrong spot or got moved around because they had to do something. The most egregious, I'll say, item that I found in my career was everyone was trying to find out why they didn't have negative air, and you just simply walked in the room and the contractor took it off because they had to put a window back and they didn't tell anybody. And so I'm like, you've got to walk these spaces routinely to make sure that things are going on. And then lastly, loading on those filters, the device trips out. We see that all the time. It trips out on the weekend or trips out during the evening, and you have no method to determine that or detect that. That's why some of these devices, such as what Josh and Emily have here, will alarm for you. Any comments on what you're seeing out there, Josh?
I think, you were spot on. First off, if you weren't getting it from the first place, you probably never had enough CFM and enough negative pressure, or your containments weren't set up right. Kind of simply, when I'm talking to someone and they're calling, they're saying, I use kind of a couple simple things. I say the door, check the machine. And by the machine, I'm saying, is the filter overflowed? Is it even turned on? Did it trip off like you talked about? Check the containment, make sure all the walls are sealed, everything's sealed. Check the building system, so the intake, the exit, the air conditioning, and then check the monitor. So the one thing that gets often misunderstood or mislooked at is the system you're using to monitor whether you're in negative. Did you set it up correctly? You talked about the hose getting clogged earlier. Is the machine put on accurately? So it's one that gets missed. These machines are not a Bible. Like, if they're set up right, they're going to work great, no matter what machine you use. But did you set it up right in the first place? Did someone pull the hose loose? All of those things. Go start from the beginning and then kind of walk from step one all the way through. You're going to find it usually halfway through that process and going down each one.
Talk about nights and weekends as well. Like, all of these things, I think it comes down to communication. And then it comes even further down to the picker process. The communication between the hospital and the contractors is usually where something's broken, and that's where something goes wrong. And like you said, Bob, someone turned something off because they thought they were finished with the project. It's nighttime. They think that you can just go ahead and shut, and so it's communication breakdowns where most of these things tend to happen.
Yeah, one thing I would love to see organizations do a better job at is not just walk into project to make sure the barrier's up and the tacky mat's in the right place and the contractors are controlling debris, but actually examine their systems that are controlling these environmental hazards. And they don't do that. I've only known a couple that do a really good job of that. One I mentioned earlier is Nemours Children's Hospital. I've worked with them in the past. They have really robust program where they monitor from the beginning to the end those machines. And so I know I mentioned this, but you get a decrease, like Josh said, in efficiency of these HEPA filters from day one. And when we start seeing a decrease in desired pressurization, which also affects our air changes, everyone just thinks, well, the machine's running, but they don't look to see that maybe your static pressure increase is out of range and it's starting to get really loaded because of kind of things that you're doing to affect it. And that's really important. So what we're trying to strive to do is when you're doing your weekly checks or your daily checks, go over and look at the machine and say, okay, guys, this is going to be out of range. You're at 1.25 inches, and at 1.5 inches, we need to change the filter out because we know by our engineering calculations, you're going to get below our static pressures, and you're going to get below what we desire for the machine. The other thing I think happens a lot of times when we have a decrease in negative pressurization is people just don't understand that these machines can't be pushed around and pushed into other areas, and they start blocking them. Just like they do in ORs, they'll block them up, and all of a sudden you see a big piece of plastic got sucked into something, and it's a problem. Now, Josh, I mentioned earlier, and we didn't really touch on it, but what's your thoughts on use of potassium manganate or any kind of different type of filtration for odors and smells? Do you get into that? Do you get asked on
Yeah,
that a lot?
no, 100%. So I think there's a couple things. I also want to jump back to something Olivia said in a second too, but um, we often see machines, especially machines that are venting out internally into other spaces, also use a carbon pre-filter with there. And if you're doing anything with smells, with chemicals, uh, that activated carbon is the game changer. Like there's no other way to put it. Having that before the HEPA, pulling and hearing those smells and chemicals, which the HEPA is just not going to affect, is super important, especially when you're going out there. Because what you don't want are patients, people walking by and they're smelling the paint from inside the room. They're smelling the varnish on the floor. They're smelling everything you're doing, all the chemicals in there. It's not great for your lungs. It's not great for anyone. And again, our goal is to maintain that what happens in the containment stays in the containment. And so we're really looking for this idea of like, what else can you add? Especially like if you're blowing out and it's not near intake or exhaust, you're probably okay. But internally, having that extra level of carbon can be super important.
Yeah, it's our rank order, and this is one thing that we preach when we're doing education is the rank order for negative pressurization machine placement is one, outdoors. Okay.
Mhm.
Outdoors away from an outside air intake. The second is if you're going to go outside and there's an air intake or a door or something, HEPA filter it. The next order is indoors to an unaffected type area, such as I can recall doing an actual OR project, and we relocated the exhaust to a solid utility room or to another
Mhm.
room in a mechanical space because that was a lower hazard. And we just didn't feel comfortable blowing this into a corridor of an OR. And sometimes you can't avoid that. Okay, we do that with the ECU units. They have to HEPA filter, and we're putting the ECU units up in like an ICU or whatever. And then the last, which is what we try to avoid at all costs, but we have to, and that's exhausting into the occupied space because we know there's so much potential. Now, if somebody came to you and said, I'm doing a mold project or an asbestos project, we would go outside. Absolutely. But if you're doing a project where there's very little risk or there's not a lot of contaminants and there's some simple dust that we can monitor, we would entertain that going inside.
And I did want to jump back for 30 seconds because Olivia brought up a point that I think is underthought of, but being enforced more and more by hospitals, which is nights, weekends, holidays. Contractors think that when I'm done for the day, I'm done for the day. They're not coming in and signing sheets. They're not auditing and doing those requirements on the night, the weekend. And a containment space is a containment space from start to finish. And we have contractors now coming to us and saying, hey, it was Thanksgiving. We didn't send anybody in. And now we're getting the IT teams coming to us and they're talking to us about why weren't we there? Why didn't we come sign this? How do we prove that we were in negative that whole time? And how do we know the machines, to your point, didn't use the automatic shut off because they got overfilled and we made that containment? So that continuous monitoring is a real challenge. And it's one that, to that communication comment earlier, is so valid and so important. If they're not on the same page with the hospital team, the facilities team, on what the expectation is, it's going to cause real problems. And we're going to see gaps. I mean, 2 out of 7 days a week, nobody's in that space checking, monitoring, making sure anything's happening. That doesn't mean those containments are still just running and moving through the air.
Yeah, one thing I hear quite often is how long should I keep my negative air machine data? Well, statute of limitations is generally 2 years, and then people can request things. I say go back to your risk manager and ask them what they need for that. My answer to that's 8 years, because I know that I've been involved with cases that have been longer than that or close to that date, and I want to be able to have that data to prove that there was no issues and be able to present it.
We've seen cases 4, 5, 6 years later where we have contractors telling me they're searching through boxes to try to find a piece of paper that was signed 4.5 years ago because of litigation. And what happens is, at least in that case, luckily they found the paper, but they also realized they were missing like 4 months of that, and they just got lucky that it was within that time frame. That's really one of the things we're trying to help and improve and monitor for. Is like, great, now it's a digital file that you have backed up, you have saved for forever, as well as one covers those weekends, those nights, those holidays where you can say, no, without a doubt, we were actually in containment. I'm never looking through paper for 10 hours a day trying to find a day 4 years ago. Hopefully we didn't get rid of it or lose that paper.
Yeah, and it's such cheap insurance to have these devices now. Here's 2026. We want devices that can give us information and can be stored.
Full pictures from the field and a wrap up as well.
Here's just some examples. On the left, I'm actually doing the measurement with a particle meter at a children's hospital that was under construction, and I'm measuring at the intake, and that's what you would do. You take the measurement of the intake as your comparison to where you exhaust. Some people, I do 2 measurements at exhaust. I do it at the exhaust of the machine on the other side at the tube, and then I also do it at the exhaust of the ductwork that goes outside, and to make sure that comparison shows a difference. And then in the middle, I'm looking at with the contractor. He's showing me this HEPA filter, and you got me thinking there, Josh. You were talking about the wood versus some of the plastics type of devices. And so, yeah, you're right. Those have to be properly seated, and then we're making sure that's going all right. And then over on the right side, on the far right, is an example of how some of these devices are actually positioned. So this is kind of the stuff we look for when we're out in the field to make sure everything's going okay.
Here's a summary of some of the questions we discussed. I think that these questions, most of these were answered, but I feel like we could talk about this for hours. It's such a pleasure talking with you, Josh, and working with you, and Emily as well. Bob, is there anything you want to say to wrap up?
No, thanks for Josh. We really appreciate you getting on the call, you and Emily. We really respect your product, and that's why we wanted to see what your take on these topics, because it's very important. Thanks again for joining us. We'll see you next time.
We'll see you next month.
Thank you, guys. See you.
Thank you. Bye.